Well, hello everyone. Good morning, good afternoon, good evening, based on the time zone that you're joining in from. Welcome back to the fourth episode of Graphversation. Super excited to talk to you this morning on the fourth episode, and we have a really exciting speaker today, Dinesh Venkatesan, who's going to talk about causal inference with knowledge graphs. More to that today in a while, but just a quick recap on what Neo4j is and what our community is. Of course, Neo4j loves community. By the way, my name is Siddhan. You can call me Sid. That's my Twitter handle that you're seeing over there. Feel free to tweet about it. I might have something for you if you tweet about it. Yes. Okay. Well, for those of you who are joining me for the first time, this is your first session. Just a recap, or rather, a quick intro on what Neo4j is and what we do as part of the community. The idea of Neo4j was conceived on a flight to Mumbai. It's a graph database and analytics company. We started in 2007. A lot of Swedish values. Our co-founder and CEO Emil is from Sweden, and he brings in those Swedish values. While we are headquartered in Silicon Valley, we started as an open source community edition, and now we have a closed source enterprise edition in addition to the community edition and the free versions. We truly believe in the open source community uh, till date. Well, yes, as I said, if you want to win this new awesome Neo4j t-shirt, you have to tweet. Just a simple thing. Just go to twitter.com, use this hashtag graphs are everywhere, and tag me and Neo4j. Yes, on how excited you are for this session. Without further ado, I want to bring in my speaker for this episode, my guest for this particular episode, Dinesh Venkatesan, who's the security researcher at Microsoft, and is going to talk about causal inference powered by knowledge graphs for applied security research. It's a really hefty topic, and we have Dinesh over here. Hi, Dinesh, how are you doing?
Hi, Siddhant. Hello, everyone. Thanks for having me. I'm really excited to participate in this conversation and interact with the community. So, yeah, super excited.
Super, super awesome, great. Thanks, Dinesh. Folks, if you have any questions, meanwhile, while we are doing this conversation with Dinesh, feel free to put them in the comment section, and we'll take them towards the end. Or if we have some time in between, we'll take them to in between as well. Uh, Dinesh, can you present your screen meanwhile? And while he is doing that, I'm going to talk about the community further. But yeah, that's I think we'll keep it for the later part of the conversation. Um, I'm sure you might have heard of knowledge graphs or have been hearing this topic, knowledge graphs, for quite some time. This is a really interesting topic for me as well. And I'm super excited to see how this conversation pans forward. So, okay, great. So, Dinesh, I have lots of questions for you. This topic is very new for me. Knowledge graphs, of course, I have heard of knowledge graphs. We work with graphs day in and day out, and knowledge graphs is something which comes as a very common topic for us to discuss internally as well and externally as well as one of the use cases for graph database. But I really love to understand causal inference first, and then want to understand how it kind of fits in the scheme of things of knowledge graphs. But before that, I would want you to talk more about yourself, what you do. Uh, like, I would love to know more about you. We had a brief interaction, but we couldn't get a time to know you much better. I just know that you're a security researcher at Microsoft. That comes with a lot of responsibilities, I'm pretty sure. But would love to understand how your journey has been so far, what you have done, and kind of also what was the first instance when you thought about graphs, like when did graphs came first to your mind?
Sure. Once again, thanks, Sid, for this excellent avenue to talk more about and to engage with the community. So, who am I? I am Dinesh Venkatesan. So, I currently work as security researcher at Microsoft. And prior to that, I have been leading security research teams at Google, Symantec, and HCL Technologies for CA antivirus. I am also a wannabe logician and mathematician who is an engineer now. Um, and I have spent the best part of the last 2 decades in analyzing malware and coming up with generic detection routines to detect malware, and writing cure for infected systems. And for the past decade, I have been working with knowledge graphs to build all the malware families that I have analyzed, so that the information is organized and it provides the right information at the right time, even without any explicit query. So these are some of the things that appealed to me uh, when I first thought of integrating knowledge graph into my work. So yeah, so that's how the journey started. Right from the college days, I started in the security industry, and then sometime around 2013, 2014, when knowledge graph became super popular, I also got super excited by the potential it offers. So from that point onwards, I have been traveling with knowledge graph along with security research.
Nice. This is great. Awesome. Like spending a decade in the like knowledge graphs and malware industry, security industry, that's huge. I think Neo4j, while the company started in 2007, I think for last decade we have been focusing a lot more on knowledge graphs. And that was the time I think when you also picked up the knowledge graphs,
Yeah.
which is great to know that there's a lot of synergies between what you have been doing and what we have also been doing. Well, yes, and also one of our viewer has mentioned Namaste Dinesh and Siddhant. So Namaste to you. I can make out what's the name of the user. It's Def Thither. So Namaste. And with this, let's move on and let's understand further on the causal inference. I'm excited to understand what is causal inference. This is totally going bouncers to me. I am very new to this entire industry, so help me understand from a laymanish terms what is causal inference.
Yeah. So I also believe in simplicity is the ultimate sophistication, and all my speaking engagements, I make sure that the talk is kind of self-contained. So I would cover from the ground up. So if some of our audiences feel that some of the concepts that we are discussing are pretty basic, please don't get offended.
Yes,
The
just
talk has
put
been
in, just put it in the comment section in the chat window if you're not able to understand anything, and we'll try our best to see how we can like not me, but Dinesh is going to try out his best to how we can kind of make it much simpler. But I'm sure he would have done a better job already to explain it in a simplified way. So let's
Yeah,
go ahead, Dinesh, and understand more on causal inference.
sure. So, informally speaking, like causal inference is basically a statistical concept. So, this can be used, or this is used to determine whether a change in something is causing a change in other thing. So
Hmm.
basically, consider you have two variables and you want to understand, if I change this variable, will this variable get changed or not? So that is a basic causal inquiry a
Hmm.
researcher can have. For example, if I change the temperature value, will the water boil? So then there is a causality between temperature and the boiling point of water. So, right.
Is
So
it more related to like a ripple effect?
yes, ripple effect is also a causal query where you observe and then you reason out, basically, by seeing that, okay, if something happens here, something happens there.
Okay.
So, and while this might sound straightforward, even for a sentinel being like human, it is sometimes difficult task to reason about something, because in most of the cases events may look like they are correlated, but that does not necessarily mean they are causally inclined. We will see more about it with some examples. Some of them are weird examples, some of them are synthetic examples, some of them are practical examples. But in general, causal inference is a process that moves from generics to specifics. So
Mm-hmm.
in mathematical term, we can call it as deduction. Say,
Okay.
for example, we have a very generic statement: all human beings are mortal. And we observe few things like Aristotle is a mortal, Plato is a mortal, and someone else is a mortal, right? So now we have got some supporting context for the original hypothesis that we have, and then we come up with a causal relation between why Aristotle is mortal, because he is a human being. That's why he is a mortal. So we started from a very generic statement that was applied to all the human beings. And then on case to case basis, we applied that hypothesis and validated whether that causal relationship that we believed holds good against the data we observe or not. So
Mm-hmm.
that is one example of how causal inference moves from a very generic statement to a specific, dealing with specifics. So like we are deducing, like a investigator may have a theory about a crime,
Right.
and how does that investigator collects additional evidences to support that original hypothesis the investigator has come up with. So it is
Got
a
it.
deducing process.
So we kind of become Robert Downey Jr. sometime. We're
Exactly.
talking about causal inference. Okay, great.
Yeah.
Cool.
Uh, Cool. So that's where I wanted to start with causal inference, and we have more to
Okay.
basically try hands-on with whatever the theory that we are discussing.
Okay.
So, for example, I believe also in applied concepts. Say, for example, now I want to apply this causal inference. Basically, I want to validate whether something is causing other thing, right? So, I have a wilting plant hanging at my balcony, and I am not sure whether the insufficient watering, whether the watering that I have been doing is causing this planter to wilt.
Mhm.
So, as I have said, I am starting with a hypothesis that says whether the water that I have been giving to this plant is insufficient, and that's why this plant is wilting, right? So, once I have this hypothesis, I have an Excel sheet that basically observes all the data associated with this plant, like how much water it is being received and what time the watering is done, and how much sunlight, say for example, high, medium, low, this planter is getting, and so many other factors as well. Now I would basically write a program using causal inference libraries and then see whether this attribute is the sole reason for this plant to wilt.
Okay.
So with that being said, I also want to cover another aspect of causal inference, which is causal discovery. So again, let's say, for example, we start from the informal session and then move to more concrete discussion
Yeah.
about it.
Sure.
So, informally speaking, again, causal discovery is a statistical concept, but this time it is used to identify causal relationship and then explore them without any prior hypothesis. So that's the key here. You can say the hypothesis, the prior to in order to have a prior hypothesis, the person who is doing the analysis has to have a domain knowledge. Say, for example, in our planter example, the person uh, should have at least some expertise in gardening to come up with that prior hypothesis, saying that it is because of insufficient watering this plant is wilting. But there are times where we may not necessarily have a domain expertise into the thing that we want to analyze, or there are times where we want to have some newly learned knowledge from observational data that has to be fed in to the process of causal inference.
Mm-hmm.
So those cases is where we start with observational data this time. If you recall, in causal inference, we started with hypothesis
Yes.
and then used observational data to validate, and to find and estimate the estimand. Whereas in causal discovery, we are starting with simple observational data, say an Excel sheet, which covers all the observational data about the subject we want to study.
Right.
And we are feeding this observational data to causal discovery program that will discover the relationships among the features or the variables that that is between each column. And that's why this process moves from specifics to generics instead of moving from generics to specifics. For example, let's recall the same mortality example, right? So now we have a Excel sheet that has an observation. Each column: Aristotle is a mortal, Plato is a mortal, Socrates is a mortal, and then we have additional data about these people. Like Aristotle is a human being, Plato is a human being, Socrates is a human being, and now we are coming up with an hypothesis that says all human beings are mortal. So here
Mhm.
we moved from bottom to up. Basically, we had an observation about Aristotle, two observations here, one that he is a mortal and he is a human being. And based on these two observations, we are coming up with a hypothesis, a theory saying that all human beings are mortal.
Right.
In practically speaking, we will not have with just two variables with a hypothesis. This is basically a dumbed down simplistic example. That's why we went quickly to coming up with hypothesis. But in general, we may have, say, 90,000 features or 80,000 features about millions of subjects, and then based on the correlation we will come up with the hypothesis.
Okay.
So, as I've said, this causal discovery is also part of causal inference process. Now, let's apply the same to our planter example. Now, instead of one simple plant, I have multiple plants,
Mm.
and some of them are cherishing, some of them are perishing. And I don't have any hypothesis because this is tough. If the watering is insufficient, why is some plant cherish and some plant perish?
Right.
So now I start with a observational data, an Excel sheet that has all the attributes, or in machine learning or deep learning terms, features about the planters, right? For example, sunlight, water, soil, genesis of the plant, and the proximity of these plants to the air cooler vent.
Yeah.
So, right. So now we pass this Excel sheet to our causal discovery. And before that, that's where our hero knowledge graph enters into the picture.
Mm.
We basically plot all this data as graph, and it helps researchers to ask right questions at right time. Because with the proliferation of data, the information is everywhere now. We have an information overflow these days. So the key is how we navigate towards asking the right questions. We will build up to this concept later in our talk. But basically, we feed this data to our knowledge graph, find correlations, find causal pathways, and from that knowledge graph insights, we construct a causal graph. And from that causal graph, we construct causal model, and then we run do calculus to observe the outputs of average treatment effect. So again, average treatment effect is a loaded term. It is basically calculating how much average effect is observed in the target variable when we change the control variable. Say, for example, in this example, if we control the amount of water and
Mm.
keep the rest of the attributes same, how much effect
Impact is.
is changed, whether it is perishing
Yeah.
or cherishing, right? So that is
Right.
ATE, average treatment effect.
Got it. This is interesting.
So yeah, so
Let
with
me
that,
link it, the casual discovery, to the knowledge graph. So but still trying to understand how. So in the previous example, where does the inference comes into picture? Is it just the hypothesis that we are kind of putting as a weighted matrix somewhere, like okay, this is a hypothesis, and we say that okay, yes, this could be the reason.
Yeah. So basically, for example, when we want to test this hypothesis, what
Hmm.
we are going to do is we are going to pick up subjects
Okay.
which share similar sunlight, similar soil, similar genesis, similar value in proximity to air
Okay.
conditioner exhaust vent, but only differing in water levels. And then we are going to see how that is going to change its growth.
Okay.
Right? So that computation can be done from observational data, or we can do controlled experiments like how it is typically done in some industries,
Hmm.
where we split into groups which share the same properties, and then we are going to water something more and water something less, and see based on this controlled experiments whether something is growing or not growing. So this is called intervention. We will
Right.
also talk about this various rung in the causal ladder later in our discussion, but this is one of the methods.
Okay. Got it. Cool. I think this sounds good. Let's move on to the knowledge graphs and see how it comes as an intersection with causal inference and causal discovery.
Sure. So, as I was building up to this slide, knowledge graph, as we all know, is a very powerful data structure, and it's an excellent mechanism to represent or store highly connected data because of the level of abstractionness it provides, and how it has a mathematically time proven theories that comes to the aid of researchers to explore and visualize and come up with additional analytics. So it's basically composed of nodes and edges, where each node is basically representing an entity, and edges represent relationships among those entities.
Right.
And the key property is like it helps researchers to ask correct questions, because asking correct questions is of paramount importance in any research field. And even experienced researchers um, sometimes need help or a nudge to in the right direction to ask correct questions in a chain of how we process. When we have a raw data, observational data, when we process that, it becomes information,
Information.
and
Right.
when we process the information, it becomes knowledge, and
Then.
that's where causal discovery happens.
Right.
And when you apply this knowledge to a problem and come up with recommendations or solutions, that's where the wisdom comes in, and that's where causal inference sits in.
Perfect. Sounds good. This is one of the best explanations I've ever seen for knowledge graph.
So yeah, as we discussed, now from this point onwards, we are going to talk about how KG fits into the whole scheme of things of causal inference and causal discovery. So while discussing causal inference, we said that a person who is performing causal inference needs to be a domain expert about the subject that we are trying to analyze. And knowledge graph is one such tool or framework which aids um, enhancing the domain knowledge. So when we want to study malware, if we have a knowledge graph of all the known malware, it will give us information about how a malware infects a system, or how a malware persists in the system. What are its anti defense techniques? What are its offensive techniques? So basically, knowledge graph will prompt the domain expert either to augment the existing knowledge or to build up a new subject in which the researcher wants to build knowledge. So it is one of the major guiding force in causal discovery, and it can both act as an input, or in graph terms as a origin node or as a sink node. For example, you can start your causal inference and causal discovery journey from knowledge graph. So gain the knowledge from the knowledge graph, transfer that knowledge into causal graph, build causal model, compute causality. Or, in other terms, you can come up with an observational data, learn the causal relationships among the entities, and represent that relationships in knowledge graph. So in this case, the knowledge graph is at the sink end. It receives from the CA and CD.
Mm-hmm.
Why is this important? Because knowledge graph, as we said, provides a lot of abstractions, and it can come up with node classification, missing relationships, and all that stuff. So it can be useful in similarity analysis, dissimilarity analysis. So it can also aid as a validation framework for the results and the observations and the learning we have got from causal inference and causal discovery.
Right.
So, in that spirit, let's talk about one more imaginary yet very associatable example, and then we will move on to real world problems. So, truth and facts, they can both sound similar, and in many places they are interchangeable, but there are places where they differ. For example, uh, truth is something which is subjective. Facts are basically objective, right? Say, for example, we can say, I'm going to use a very technically loose statement here just to make the example more relatable. Say, for example, we can say um, 2 plus 3 is equal to 5, right?
Right.
So we can say this as a fact because 2 plus 3 is always equal to 5.
Yeah.
But if we reverse, 5 is equal to 2 plus 3, while this
Mm.
is true, 5 can also be equal to 4 plus 1, or 7 minus 2, or 8
Yeah.
minus 3. So there are a number of ways you can tell that, right?
Correct.
So let's put on that kind of thinking hat and then say, I have a observational data Excel sheet which talks about a person and their performance against a computer playing chess. And there are so many attributes. Each attribute is represented in one column. Say we have shoe size of the person, we have the height of the person, we have the gender of the person, we have the geolocation of the person. These are properties about each person. And then
Yeah.
we have a final column that says how do they play against, or how many wins do they have against a computer playing chess.
Mm.
So, in
Okay.
this observation, it can be seen that people having bigger shoe size are playing better against a computer. Again, this is a very hypothetical data. I'm just giving it as an example, right?
Yeah.
So now, while this association is there to see in the data, it does not make sense. How is having a shoe size, wearing a larger shoe, result in better win against a computer playing chess? So this is called spurious associations, and
Mm.
that's where there is an important concept called confounder. Say if we take a deeper look at the data, we may observe that there is another variable called age, which affects the shoe size.
But we never taking into account.
Yeah, even if we take into account, we should not be taking shoe size into account as a causal relationship.
Yeah. Got it.
And this age is a confounder variable that affects the shoe size and is also affecting the number of wins. So once we put this realization, this spurious relationship will come to the picture.
Mm.
So
Okay.
then we come to know that it is not because of wearing a bigger shoe you can win against a computer. It is because as the age becomes higher, the practice, the knowledge someone gains from playing again and again with the computer increases, and thereby the number of wins increases. So here is the causal query, and that's where this wonderful ladder of causation it's basically a Perlian perspective, which talks about the different rungs in a causal ladder. So we have three rungs. The first rung is observation, which is simple association. We have a Excel sheet with different columns, each column representing one feature of the subject we are studying, and we simply observe, like how we have seen shoe size is associated. I am carefully using the word associated here. It is not causing, it is simply associated with the victories.
Yeah.
And the second rung is basically an action rung where we intervene. Say, for example, let's take a weird example. We play against a computer wearing a bigger shoe. Does it make me perform better against a computer? No. So it's intervention, right? Like randomized control trials that we talked about. Those kind of stuff. And the third rung is it's a very high rung in the causal ladder, which is imagination, counterfactuals. So counterfactuals is a stage where we will not be able to do these experiments for various reasons.
Okay.
Say, for example, what would have happened had I moved to XYZ place 5 years ago? Now I cannot go in reality, go back in time and change that I move from one place to another place and then observe what would have happened had I moved. But we can use counterfactuals. There are libraries, there are methodologies using which we will be able to study that. So that's the very highest rung in the causal ladder.
Got it.
So, like you brought up Robert Downey Jr., Sherlock Holmes.
Nice.
Yeah, he was famous not only because he had the power to deduce, he also had the power to induction. Like he was able to go from generics to specifics, and then from specifics to generics. Like
Yeah.
he collected evidences. Based on the evidences, he came up with hypothesis. So, like as I said, we have discussed theory a lot. So, and some simplistic examples. Now let's
Yeah,
get
I would love to know the actual thing in action, because
yeah,
this looks pretty interesting in theory, but does it really work
yeah,
like in principle as well, in reality? That's what I'm curious as well now. I loved the entire explanation. It was good.
yeah. So let's put our programming hats and see some of these things in action.
Okay,
I
great.
am going to try running these programs in live, and if something goes wrong, probably we have a video demonstration as well.
Sure.
So yeah, so we are going to perform causal inference now. So you can see here. So this is the observational data that I was talking about.
Can
Again,
you,
these
sorry, Dinesh, can you zoom in a bit? Actually, it's not readable enough.
sure.
At least we know what the headers are if we don't understand even
Yeah,
the. Okay,
yeah.
this is
Is this
age,
better?
calorie intake, income, education, exercise hours, and weight loss. Okay, perfect.
Yeah. Okay. So again, these are highly compute intensive processes, crunching data features and then coming up with reasons, causal analysis, and basically deep learning, machine learning.
Okay.
So in
What are
order to,
these features?
yeah,
Sorry, Dinesh. Another question. What are these features related to? As in, what are we trying to solve over here? What is the
yeah.
final outcome that we are looking for?
That's a great question. Say for example, this Excel sheet, every row is about a person. So
Okay.
person A, person B, person C, and then every column is about a property or a feature of a person. Like what is the age of the person we are talking about? What is the calorie intake of the person? What is the person's income? What is the person's education? And what is the exercise hours of that person, the daily exercise hours, and how much weight loss has been observed with this person. So a
Okay.
negative value indicates the person has gained weight, a positive value indicates the person has lost, for example, in this case 5.84 kg weight. uh,
Okay.
right. So again, in order to make this program running in real time, because generally very high compute intensive program with lot of features, these 7 features are never going to be enough. because in real world we will have so many other factors influencing this whole journey, and there will be so many other people. Like only 1,000 people is not a good data set. So if
Mm.
we put all those stuff in this particular program to consume the data, probably it will run for 1 or 2 hours. So in order to make it run in a very short span of time, we have cut down some of the features and only taken a small data set.
Okay, got it.
So yeah, so now we have also, as I have said previously, we have ingested this in a knowledge graph.
Can you zoom this? Yeah, thank you.
So
While you're doing that, I have a question in terms of how you are converting education into numerical value.
yes, that's an excellent question again. So where is this? Yeah. Okay, again, this needs to be zoomed up.
Yeah, the the script is quite tiny. I think there should be an option to increase or
Yeah,
zoom.
basically this is my virtual machine. So the text editor here I have is not the one which I use. Yeah, here it is.
Yeah, and there the size. Yeah, this.
Okay.
Perfect.
So, so for this is a POC, so we are just doing a simple categorization. Like if this value falls between this range and this range, consider it as low calorie intake, medium calorie intake, higher calorie intake, and similarly education category low, medium, high. Weight loss categories we are splitting into 7 categories: high weight loss, high weight, medium weight loss, low weight loss, high gain, medium gain, low gain, no change.
Okay.
Similarly, young, middle aged, old. So it's basically categorization.
Okay.
So again, this is a demo thing, so that's why you see the password in plain text. Otherwise, it is not recommended to keep all these things in
Right.
basically a demo machine, virtual machine, kind of a throwaway machine. So yeah. So with that said, we ingested the Excel sheet into our new 4J backend, and we have all the people and their data related to that person as a graph, and everything is all set. Now, first let's see the causal inference in action, and again we will go back to the specifics of it. So now what I'm going to do is, as I have said in the very first slides, now I'm playing the domain expert role, and I believe exercise hours has a causal effect on weight loss. So now I am going to calculate average treatment effect,
Mm-hmm.
where the target will be the weight loss and the controller variable is
Exercise.
exercise hours. So how much change in exercise hours is going to cause change in weight loss? So
Okay. Nice.
yeah, so let's run this program. So as you could see here, we are keeping exercise hours as control variable and keeping everything else as the same. So the mean value we see here is 2.14. That means
Right.
1 unit of change in exercise hours causes 2.1 kg weight loss because it
Mm.
is positive. When it is positive, it is weight loss. When it is negative, it is weight gain.
Mm.
And
Okay.
a very important process in causal inference is also to do refute analysis. So we may want to introduce some methodology that will challenge our discovery. So basically, what we are trying to do is the program is adding a random common cause and then tries to perform the estimate again and comes up with a value. And the higher p value suggests that uh, the closer it is to value 1, it is null hypothesis. That means the
Mm.
refutal has no ground. So that
Ground.
means whatever the causal assumption that we had is valid,
Right.
right? So now let's go back to knowledge graph and see whether what the program says has any support with the
Okay.
data, right? So let's run this query.
Wow.
So now you see what we have done here is we are querying the Neo4j backend to give people who have high weight loss, low weight loss, and medium weight loss, and no change. At the same time, they have done exercise, right?
Mm,
So it gives this nice graph.
yeah.
It has to be zoomed in again, but let's see whether
I
we can.
think there's a zoom button down below,
Yeah.
on the right. No, no. Yeah, this one. Perfect.
Okay. So this orange nodes are basically weight category. So this one
Right.
is, as you could see here, click on
Three, wait,
it.
four,
This
one,
is low
loss.
loss, a low
Yeah.
loss. Right? So people who have exercised more, they either gained a low weight loss. Again, the terminology is little tricky. Low weight loss does not mean negative, because
Yes.
weight gain is negative in this case. Here, no change. Some people, even after exercising, they don't lose weight. We'll see more about it. And there are these set of people who have gained high weight loss because of exercising, and there are few people who have neither gained nor lost any weight. Now
Right.
let's bring a different perspective and query about people who haven't exercised.
Right.
I change 1 to 0. Now rerun the query. Now you see, there are so many people with no change category. There are so many people with low
Low
weight
loss.
loss category, and there are some people who have medium weight loss category. Now, in order to make it crystal clear, let's run the query, but this time we will not focus on people who have lost less weight or medium weight or in the no change category. We want to inquire about people who have accomplished high weight loss without doing exercise. And as expected, there are no records because the people who haven't done exercise, they haven't lost any weight.
They
They
lost.
haven't accomplished high weight loss. But let's run the query with exercise.
We saw something last.
Yeah.
Yes.
So these are the number of people. Every 415 is a person, 446 is a person. You can expand it to no more. So these are people who have gained, who have accomplished high weight loss and have exercise as one of their regular routine.
Right.
So that is what we meant when we said knowledge graph can act both as a domain expert who is feeding into causal graph and as a validator or as an observer who takes the output of causal output and then see it in action against the multiple entities.
Got it.
Okay, so with that said, I think now this demo is not recorded. I basically created it, so let's skip that. And now that brings us to causal
Awesome.
discovery.
Yeah.
So the causal discovery in action is again the other step that we talked about, right? In causal discovery, we are going to start with observational data and then come up with causal structure. So to explain this more, let me open up that same example. So if you
Okay.
see here, in the infer cause example, we have given common causes. So the statistical term for this is confounders. Like recall the example we gave for the people playing chess. So where there are age is a confounder, right? So similarly here, in order to weight loss, exercise hours has a causal effect on weight loss. But at the same time, there are few more confounders like calorie intake affects weight loss,
Mm-hmm.
education affects weight loss, right? So this in this observational thing. So this graph, basically this is a graph. This is a directed acyclic graph. So this is called the causal graph. So this causal graph came from domain expertise, and we used this causal knowledge graph to build causal graph, and use this causal graph to build our causal model. But now, what we are going to demonstrate is how to learn this causal graph. Basically, we are going to do causal discovery. Again, this will not be a perfect process because in real world data, it is not often you will find a perfect causal relationship just by observing the data.
True.
Uh, in order to augment it with an working example, I am going to use this library.
Julia.
Yeah, so we are going to use causal inference library from Julia to discover cause. So in this program, we have not defined the causal structure. Instead, we let the Excel sheet go into this program and come up with causal structure. So it says calorie intake is affecting exercise hours, so on and so forth. You can also observe the imperfection I was talking about. So
Mm-hmm.
this program, because the data set is small and because the features are considerably lesser, it tells us that weight loss is affecting exercise hours. It is actually the other way around. Exercise hours is affecting the weight loss. So even though we have got some useful information, it is not perfect, as I have said. So in a real world with lot of observational data, with too much compute power, it will be perfect. But in it will not be perfect again. It will be better. But this is just to demonstrate like what is causal discovery, right? So again, coming back to the tangent, so finding spurious association is easier when the domain is trivial, when the data set is small, when the factors are lesser. In case of a chess example, it was glaring to spot that spurious associations. In any real world problems, it won't be as easy as picking it up just from looking at the Excel sheet.
Right.
So that's what we have a security research use case here now. Now let's run. So in this case, again, we have taken a very small example that basically talks about an malware and then 5 attributes about the malware, like how many loops are present in the code, what
Right.
is the malware family, how many conditional statements are there, how many functions are there, and how many syscalls are there. And we are going to perform ATE on the number of syscalls against the file size. So in
Okay.
this case, each change, each increase in the number of syscalls causes 1 kilobyte decrease in file size. So that's what
Uh,
you see here. And the p-value, it is closer to 1. That means our refutal analysis also comes up good. And that says that the causal estimate the program has identified is good, quite good.
okay.
So that's what we applied it on a real use case. Again, as I've said, in a larger set, there will be thousands and thousands of features against millions of samples. But here we are running on 100 sample with 5 feature set.
Got it.
So, so basically, what we are trying to accomplish here is we see an executable from different vantage points.
Okay.
From static analysis, we just do automated reverse engineering and list all the parameters that we identified from static. And we also run the program and see whether all the observations while running the program, how does the program behave? And we tabulate those results also in the Excel sheet. And we also do DFIR, digital forensics in the incident response practices, such as capturing the live memory, inspecting the kernel data structures, coming up with all the artifacts, tabulate them. And now we have three different vantage points from which we have observed the set of executables, the malware samples, basically
Okay.
our viruses, trojans, worms. And then we are plotting all these data points into knowledge graph to come up with the domain expertise that we are talking about. And that combined with human expertise, we build causal graphs, we build causal models, we feed the observational data, and deduce answer causal queries. So let's quickly see some of these things in action.
Okay.
And we are also coming close to
Yeah.
yeah. So yeah, let's speed up this video a bit. So now what we are trying to do is we have taken a bunch of Android malware samples, and we are trying to plot them. So initially, as you could see, there is no information available in the graph. Now we are going to use our parser to parse the malware samples. As
Wow.
it is parsing, it also populates the backend. So now all the information about this particular APK is loaded into the knowledge graph. So we have a ransomware sample loaded into the backend. We'll run one more sample and one more sample. Now let's navigate the static analysis graph. Basically, all the
Mm,
static information available from this graph. What are the methods it calls, and what kind of resources these programs access, and all that stuff. And basically, I also wanted to take this opportunity to see how knowledge graph can contribute. So we are going to use neo4j data science libraries, graph data science libraries, and compute similarities based on the call chains. So now when you run the next query, you will see that how one node is similar to another node. It is basically how one APK, Android program, is similar to another Android application. So you could see here it has 0.46 similarity, which is 46% similarity. This is 1% similarity. So this kind of induction can go hand in hand with our causal inference and causal discovery programs in a real world scenario to come up with the intel that we wanted.
got it. Interesting. This is great,
Yeah.
Dinesh.
So yeah. So at this stage, probably I want to take a pause because we have talked about a few loaded terminologies and examples, and would like to take any queries from the audience or from you
Yes.
to
No, I
make it.
think pretty much good to me. I have a couple of questions, although from the from our uh, viewers. And there's one question from Dixon Lucas. He's asking, did you do all the causal inference and causal deduction outside of Neo4j and use Neo4j for displaying the results? Pretty good question.
Yeah, that's a great question. So when we said the outside of the Neo4j realm, that program is actually taking a graph as input. So that input comes from Neo4j. So it is kind of a pipeline. You can visualize it as a pipeline. So the data sheet, the Excel sheet is feeding into Neo4j. Neo4j is outputting the graph, and that goes to a human evaluation. Along with the human input, it goes to causal inference program, that particular program that takes the common causes as a graph, and then it produces the output. Again, that goes into loop. The discovery of causal inference program loops into the along with the observational data passed to knowledge graph, performs similarity, dissimilarity analysis, clustering, and validates and provides support for the discovery. So it's basically a pipeline with loop.
Great. Thank you. Thanks, Dinesh. I hope, Dixon, that answers your question. If not, then if you have any follow-up question, just mention in the comment section. This next question from Deft. He's asking, Dinesh, do you have a public code repository with some samples of causal inference powered by KG?
Yeah, but I think after today's talk, it will be live. Probably I will share the link in the comments.
Yeah, or probably just Dinesh can share with me, and then I'll add it in the
Sure.
description of this video
Yeah.
along with the slide deck. So if you want to have a look at it later on in future, you can always go back to the description section and like glance through it. Cool. Okay, we have just 4 minutes left. If there are more questions out there, we can take up, or I have just last few things to talk about. This was really, really great, Dinesh. Thank you so much for doing this. I really enjoyed the conversation. I learned a thing or two today. If not everything, I need to get my hands on and then start working on it. But I really enjoyed the entire bit of conversation that we had today and understood something about causal inference and working with knowledge graphs. Great. Do you have any last comments, any thoughts, anything that you would like to share with me, with the people who are listening to us?
Yeah, like thanks again, and it's a wonderful community. So I enjoy taking part in community discussions, and I'm looking forward to network with people as well who have great interest in this domain, and looking forward to it. Any queries, please feel free to reach out to me in the social media as well. So yeah.
Yeah. And if you wish to continue your graph journey, this is just a glimpse of how big and exciting this entire industry is. If you want to continue your graph journey, you can do it with the Graph Academy. We have these amazing, self-paced, hands-on online courses, specially curated for you. And there's a curated learning path as well, where you can pick in based on your interests, pick in a path, and then start using those courses, putting those into practice. And to test your knowledge, we have these two certifications as well. One is Neo4j Certified Professional, another one is Neo4j Graph Data Science Certification. So take a test of your knowledge if you already know about graphs. Go ahead and take these certifications and show us on social media of your achievement. Okay. Next thing I want to talk about is Notes 23. It's a virtual marathon of graph content that we are bringing back this year. We've been running this for quite some time, over three time zones: America, EMEA, and APAC. And we'll be having APAC specific content as well, APAC specific time zones as well, from beginner to intermediate to advanced. It all connects over here. So make sure you register for notes, dev.neo4j.com/notes23. If you want to submit your talk as well, that's a great thing and would love to hear your talks. So you can do that as well by 30th of June. Again, just go to the same URL and you'll find the link to both register and submit your CFPs. But don't forget to save the date, and I'll see you on 26th of October as well. Okay. Next thing, while we're doing this virtual session, this Graphversation, and this APAC training series that we recently concluded, all those will be available on our YouTube handle. But if you wish to connect further with us, meet like-minded graphistas, uh, have a connect in these in-person meetups, hack around things, build cool products together. Well, this is a great opportunity for you. Just go to meetup.com/pro/neo4j, and we have, I think, 36 groups across 18 countries that you can join, attend these meetups, be part of it, stay updated, and stay curious. And if you wish to speak at any of our meetups or the next episode of Graphversation, this is one thing which I would like to call out. This is a very small form. Just go to dev.neo4j.com/submit your talk. Interesting thing, I got to know about Dinesh via this form itself. Um, Dinesh, curious to know, how did I get to know about this form? Was that a newsletter?
Yeah, I was speaking in Notes 2022. So during that juncture, I got this
Nice.
meetup. Yeah.
Great, great, awesome. And you too can take a like take a stab at it and make best of use of this opportunity. Uh, so go ahead and fill this form, and I look forward to seeing your entry in the form, and then I'll contact you as soon as possible. And last but not the least, let's stay connected with the community. If at any point of time you face any queries, you have any questions for us, while we are there available on social media, but you can always put your technical queries in the Discord or Discourse forum. So, whichever you want to go ahead and sign up for, just go ahead and put your questions over there, and we'll answer it as soon as possible. The URL is dev.neo4j.com/chat. That's for our Discord channel. And dev.neo4j.com/community is our community forum on community.neo4j.com. So go ahead and sign up for it and ask questions. Ask so many questions that we get pissed off that you are asking so many questions, but no, we will not. But yes, keep asking, keep interacting, and keep graphing. With this, we'll wrap up today's session and also this episode of Graphversation. Hope to see you soon in the next episode of Graphversation. We're gonna announce it pretty soon. It's happening in the month of July. The date is going to be announced soon. So look forward to the next another content, another speaker, another guest, another day, another month. Yes. With this, signing off for the fourth episode of Graphversation. Thanks so much, Dinesh, once again, and thanks to all of you out there listening to us till now. Thank you. Bye.
Bye. Thank you.
The broadcast.